The next model predicts log sleep based on both vor and log weight. First, we'll remake the graphic that we made initially. There's no legend here, but the idea is that we have log weight as a predictor on the x-axis, and the points are colored to represent different possible vors. So if we're going to run a linear model, the assumption we're making, if we don't include an interaction, is that for each color we think there's a line connecting the mean log sleep with log weight. So if you look only at the red dots, we think there's a line. If you look only at the black dots, we think there's a line. If you look only at the dark blue dots, we think there's a line. And if we don't include an interaction, the assumption we're making is that those lines are parallel. Now, I think that's probably not quite true here, but we're going to run the model anyway. Note that if we round log weight to make it a little bit less continuous, then we can also make box plots for all the different combinations of vor and log weight. Now, this is not particularly interpretable. There's a lot of different combinations because there are a lot of different possible values of log weight, even when it's rounded. However, the point of making this graphic at this moment is just to show you, remind you, that even for a multiple regression or a multiple ANOVA with multiple predictors, all we're doing is trying to come up with a way to specify what we think the values of y will be for any different combination of x's. This time we'll start with an ANOVA, so I'm going to call it M3 because it's the third model we've run, and AOV because I'm going to use the AOV function to predict log sleep given vor and log weight. And then I'll summarize the output, and of course it'll be summarized in the usual ANOVA format because I used AOV. So looking at these results, we see that we have both vor and log weight listed here, and then residuals. Now depending on what you've done before coming to this video, you may or may not have seen an ANOVA with multiple predictors in it before. But the basic idea is the same, that we are going to take the total sum of squares and divide it into sum of squares that's due just to residuals and sums of squares that are due to the various predictors, and if there are multiple of them, then all of these sums of squares, all three of these, should add up to the total. So we're taking what we've been calling the sum of squared model, and we're dividing it into the portion of that that's due to the vors having different log sleeps, and the part that's due to the log sleep varying by the log of weight. You also see here that we have p-values for f-tests, and we'll talk more about those as we go on, but the idea is that we are trying to assess how surprising the data would be if these particular predictors were not included in the model. Just as before, we have residuals and fitted values, and we can plot them, so we're just going to make that plot so you can see that we can do it. Right? And this suggests perhaps this model doesn't fit all that well. This is not a great residual plot, and I'm not shocked by that because when we looked at the initial plot, it looked to me that if you focus just at the points of just one color, the lines did not appear to be parallel. So it's not shocking to me this model doesn't fit particularly well. Importantly, again, repeating what we talked about in the last video, log weight here is continuous, but we're still running the ANOVA. When you look at the ANOVA output, you can look at the degrees of freedom to see for any predictor that's categorical, the degrees of freedom will be equal to number of categories minus 1. For any predictor that's continuous, you'll see just a 1 here. So that's a way to check that a predictor you thought was continuous really is being handled as continuous, and vice versa. As before, we can derive the sums of squares shown in the output of the ANOVA using the residuals themselves. So if we take the residuals from the ANOVA, square them, and add them all up, we're going to get the sum of squared residuals, and I'm calling it SSR.3 because it's the third model we've run, and this 11.88 is the same value we have here for the sum of squared residuals. So that's good. We were able to verify that value. If we take the vector of log sleep values, subtract from each of them the mean of the log sleep values, and square them, add them all up, that's the sum of squared total, the overall sums of squares, assuming we have an equal means model or no relevant predictors. So we can get SS total. And just by definition, if we take the SS total minus SS residual, we'll get what we've been calling SS model.